Playing time, let us begin. The number system defines, one second. Okay. Uh, Give me 1 second, I'm coming. All right, sorry about that. So, the number system is what we are going to discuss. And in our discussion with the number system, in our discussion with the number system, we are going to look at decimals, we are going to look at binary, we are going to look at hexadecimal numbers, and we are going to briefly discuss what these type of numbers are and how we can utilize these numbers in the things we are going to do later on. As discussed last week, we saw that if you have a computer, the voltage that comes into the system is what we use to measure if it is on or off, hence if it is true or false, or hence if it is a zero or a one, where a zero and a one means it is on or off. Hence, the numbering system of a computer is said to be binary. It's said to be binary. So that is the numbering system that the computer uses. The numbering system in which we use is said to be digital, or is said to be decimal, or in base 10 form. So that's the number system in which we use. Our understanding goes like that we need to learn the various data systems that the computer utilizes. It utilizes binary in its basic form and moves on to utilize hexadecimal numbers so that it can take a larger group of numbers to do or implement some of the things it wants to implement. We as the users, we use decimal numbering system in order for us to do our banking, communicating, calling people, and do all of that. Hence, we must learn how we can convert from each of these numbers back and forth, which will allow us to have an understanding of what we are doing. And it will allow us to know how we can tell the computer to make the conversion of the numbers back and forth. So let's start with the binary numbering system. The binary numbering system is also called the base 2 system. The binary numbering system is used to model the series of electrical signals computers use to represent information. 0 represents the no voltage or an off state, and 1 represents a voltage or an on state. And we have explained that into detail. So what are the characteristics of binary numbering system? Number one, it uses zeros and ones. Of course, all of its communications come in zeros and ones. So it utilizes zeros and ones. Also, it is called the base 2 numbering system. Each position in a binary numbering system represents the power of base 2. For example, 2 raised to the power 0. So if I have any number raised to the power 0, it is a representation of what I have. Let's see if I can put it this way. 2 raised to the power 2 raised to the power 0 would be 2 2 itself. Then 2 raised to the power 1 would be 4. 2 raised to the power 2 would give you 8. 2 raised to the power 3 would give you 16. 2 raised to the power 4 would give you 32. So the positioning of these words here, the same way, if you have base 10, then I would say the first one is in ones, the second one is in tens, the third one is in hundreds, the fourth one is in thousands, then so on and so forth. That is the same one in binary. The first one is in ones, the second one is in twos, the third one will be in threes, the fourth one will be in eights, so on and so forth. So over here, we have a diagram showcasing the binomial numbering system. We have 0, 0, 0 being equivalent to 0. We have 0, 0, 1 being equivalent to 1 in our numbering system. We have 0, 1, 0 being equal to 2. We have 0, 1, 1 being equal to 3. We have 1, 0, 0 being equal to 4. We have 1, 0, 1 being equal to 5, and so on and so forth. So all of these things here are representatives of the binary numbering system. And as an add-on, as you can see on the side here where we have the green, we are seeing that if it is 2 raised to the power 0, then you have ones. If it's 2 raised to the power 1, then you have twos. If it's 2 raised to the power 2, then you have fours. If it's 2 raised to the power 8, then you have eights. These numbering here show the positional value of the thing. A best good way to explain the positional value of the thing would be this. So let's say I have two that have something like this. The positional value of this 5 is what? Ones. The positional value of the twos is tens. The positional value of the 1 would be hundreds. So this is the numbering system that we use so that I can say this is 100, 2, 20, and what? 5. That is how I would see this and recognize this. But if I have 0, 1, 0, 0, 0, 1 like this, that means that this one here, let me put a 1 here so that it's more clearer. That means that this one over here represents the 0. The 0 we have here represents the twos. Then the 1 we have here again represents the 4s. Then the next 0 represents the 8s. Then the next one will represent what? 16. So that is how we would represent them using the binary numbering system. Please, are there any questions so far?
No, please.
That's wonderful. If there are no questions, then let's continue to the decimal numbering system. Now, the decimal numbering system has base 10 as it uses 10 digits from 0 to 9. In the decimal numbering system, the successive positions to the left of the decimal point represent the units, tens, hundreds, thousands, and so on. And this I have already explained, whereby if I have a digit in the first cell, for example, let's take this one over here and come into the plain screen and see if we can break it down. So if I have this 4 over here, technically, is 4 times Okay? Ten raised to the power 0. Now, 10 raised to the power 0 is going to give me 1. That means I have 4 times what? 1. So this is going to give me what? 4. That's understandable. If I go and take the 3, it is 3 times 10 raised to the power 1. 10 raised to the power 1 would give me 10. That means I have 3 times 10 being equal to 30. Then if I have 2, it is the 2 times 10 raised to the power 2. That technically means 10 times 10. And this would give me 2 times 100. So this is how you break down the various positional digits of the decimal numbering system. The same way we did for the twos. Let's go to the hexadecimal numbering system. Now, under the hexadecimal numbering system, I'm looking at a scenario whereby I have from 0 to 9. Now, after 9, I can't repeat digits. If I do 1, 0, it means that I'm repeating the digits again. So I can't do that. So it means that when I get to 9, the 10th thing becomes A, the 11th thing becomes B, the 12th thing becomes C, the thing after that becomes E, and the final thing becomes F. Because if I do 1, 0 for base 16, that is the hexadecimal, it means that I am repeating the value and it has a value. The same way in which the value over here, when I have 3, 0, I'm saying that 3, 0 is 3 times 10 raised to the power what? 1. So if I go and write 1, 0, it means that 0 has a value, and then the 1 also has a what? Value. And that would make my answer wrong, because each position has a value. So I can't tell the computer, or I can't write out that, okay, if you have 10, then it should be 1, 0, because the 0 is over here already and the 1 is over here. So it is me adding values. So it means that everything should be 1 digit. Hence, the 10 for hexadecimal is going to be A, and then the 11 is going to be B, the 12 is going to be C, the 13 is going to be D, then E, then F. Do we understand this? Are there any questions? Wonderful. So, what are the characteristics of a hexadecimal? A hexadecimal uses 10 digits and 6 letters to represent its numbering system. We have seen that already. So you have 0 to 9. Then when you get to 9, the 10th thing is going to be A, 11th is going to be B, the 12th is going to be C, the 14th is going to be E, and the final thing, which is F, is going to be 15, so that is how you have your numbering for the hexadecimal system. So if I go and see 1A, technically, I'm writing 26. So the A there has a value that is used to represent itself. So let's understand some things. Whenever I say something is a binary number, then it means I'm talking from 0 to 1. Whenever I say something is an octal number, then that means I'm talking from 0 to 7. When I say the thing is decimal, then I'm talking from 0 to 9. When I say the thing is hexadecimal, then I'm talking from 0 to F, where it will stop at 9, and then the 10th thing would be A, 11th would be B, 12th would be C, then E, then what? F. Is it clear, please?
Yes, please.
Okay. So now let's talk about the significant bit. And what is the significant bit? So say a bit, then there is a value on it that we need to note. For example, if I take a binary number like this, okay, the most significant bit is the digit that is on its far left-hand side. So over here on the far left-hand side, the one over here is the most significant bit. So here, this one here is the most significant bit. Over here, the least significant bit is the digit we have on the right-hand side for my screen. If I go and take a hexadecimal, I can say the most significant bit is which one? Who can tell me? Who can tell me which one is the most significant bit? Any takers?
The one.
The one. And the least significant bit is which one?
The A.
The A.
The A. So that is what we have over here. Now, in your exam, I could bring something like this in the section 8 without write equation and tell you which one is the most significant bit, which one is the least significant bit. I expect you to know these two things. Now, why are these two things important? They are important because if I want to do binary conversions, that is, I want to change from decimal numbers to binary numbers, knowing which one is significant and not is very important to how I am going to solve the question. Now, for binary conversions, I have base 10. I want to change from base 10 to binary, to base 2. Over there, I have 64. So I want to change from 64 to its equivalent in base 2. How will I do this? So I will divide by 2. 64 and 67 divided by 2 would give me 33. With a remainder of what? 1. So I will keep note of the 1, and then I would move on to divide it again. 33 divided by 2 would give me 16, with a remainder of what? 1. Sorry, 33 divided by 2 would give me 16 with a remainder of what? 1. Just so that we are clear, let's see what I mean by this. If I go and take my calculator over here on the screen, and I say 37 divided by 2, I would get 33. So it means 2 times 33 would give me 66. So 66 minus 67 would give me 1. So I have a remainder of what? 1. So when I say remainder of, it means that when this divides this, 33 is the whole number side I will get. the whole number side. Then the remainder of the number that is not part of the whole number, I have to find that too. So I'll just multiply 2 by the number and then subtract by the number, and I'll get what? 1. To be honest with you, when you're dealing with binary, most of the time you either get a 1 as a remainder or you not get a remainder at all. Like here, 16 divided by 2 would give me a remainder of 8 and a value of, I'll give me a value of 8, but there will be no remainder. So my remainder would be what? 0. 8 into 2 into 8 would give me 4. No remainder. 2 into 4 would give me 0. No remainder. Then 2 into 2 would give me 1. No remainder. So I would stop when my coefficient reaches 0. So 2 goes into 2, 2 goes into 1, 0, and I have a remainder of what? 1. So this is what I have. That is 2 times 0 give me 0, and what will remain? 1. Now, after I get this, moment I get to 0, I can't go anymore, so I'm stuck, I'm finished. So I need to write out my answer. In writing out my answer, I will start from the most significant bit. So I have 1, that is the 1 at the bottom here. So 1, 0, 0, 0, 0, 1, 1. So the most significant bit is here, and then the least significant bit is the one at the top over here. Let's see if I can go through this again, just for posterity's sake. I have 67. I want to convert from a decimal base to a binary bit. First thing I need to do is find its coefficient. So 2. When it divides 67, what will you get? You will get 33, and there will be a remainder of what? 1. If you take 33 and you divide by 2, you will get 16, and there will be a remainder of what? 1. If you take 16 and you divide by 2, you get 8, but there will be a remainder of what? 1. 8, 0, because there will be no remainder. It cancels out perfect. If you take 8, it will go into it 4 times, but there will be a remainder of what? 0. If you take 4, it will go into it 2 times, and there will be a remainder of what? 0. If you take 2, it will go into it once, and there will be a remainder of what? 0. Now, if you take 1, 2 times 0 would give you 0, and there will be a remainder of what? 1. So you get what? This. When you're done, then you'd write your answer, only the remainders from the bottom to the top, where the bottom becomes the most significant bit, and then the one at the top becomes the least significant bit. So this is what you would what? Get. Is it clear, please?
Yes, please.
So if I have a binary number and I want to go to a decimal number, how will I convert it? For example, I have this binary number on my screen, 10101101. How will I convert this into a decimal equivalent? So I'll write my binary number down. After writing that, I would go and write the positional values of the binary numbers. So the positional values are as follows. For the first one, it is 2 raised to the power 0. Second one, 2 raised to the power 1. Third one, 2 raised to the power 2. 2 raised to the power 3, and so on and so forth. And we saw that when we began the course, whereby we see 1, 2, 4, 8, 16, and so on and so forth. I would multiply the binary number by the positional value. So it means that 1 times 2 raised to the power 0 0 times 2 raised to the power 1, 1 times 2 raised to the power 2, 1 times 2 raised to the power 3, 0 times 2 raised to the power 4, 1 times 2 raised to the power 5, 0 times 2 raised to the power 6, 1 times 2 raised to the power 7. The answer of this would give me this. Then I would add them all together. After adding them all together, I will get my answer in what? Decimal. Are we clear on this, please?
No, sir, Mr. You go over again.
I have to go over again. Oh no. I have 10101101 in binary. And my job is to convert this from binary to decimal. How will I convert this from binary to decimal? First of all, I have to take the positional values of the elements. In the slides, we talked about positional values over here somewhere. So when I got here, I started talking about the positional values. Why I said that if you have a digit, the first one is a 1, the second one is a 2, the third one is 4, the fourth one is 8, the fifth one is 16, the sixth one is 32, the seventh one is 64, and the last one is 128. Now, how did they get the 1, 2, 3, 4 things at the bottom over there? What they did was they did the powers of 2. So it means that if I'm writing this again, right? So I'm here, I'm writing it again. I'll have, starting from the end, I'll have into brackets 1 times 2 raised to the power 0. So that is for this one here. The next one is me having 1 times 2 raised to the power 1. And here would be 0. And they will be adding together. So it means that I'm done with this one is for this. This one here is for that. I'm coming to the next one. With the next one, I have 1 times 2 raised to the power what? 2. I'm going to the next one. I have 1 plus 2 raised to the power 3. So I'm done with this one. Then over here, I'm going to, so I'm done with this one, right? So I'm going to this one. So I have 0 times 2 raised to the power 4. Then I also have this one here times 2 raised to the power what? 5. Then I have this one here plus 2 raised to the power what? 6. Then finally I have this one plus 2 raised to the power 7. Now, 2 raised to the power 0 is 1. 2 raised to the power 2 would give me 2. 2 raised to the power 2 here would be 4. 2 raised to the power 3 here would be 8. 2 raised to the power 4 here would be 16. 2 raised to the power 5 here would be 32. 2 raised to the power 6 here would be 64. And then 2 raised to the power 7 over here should be 128. If I've not made, have I made a mistake with this one? Let me see. Let me go and check. Oh, I didn't. I'm correct. Now, 2 raised to the power 2 over here would give me 0. So this one will go away. And then this one will also give me 0. So it will also what? Go away. I think there should be another 0 somewhere here. But let's come back to the slide because I think we are okay with the understanding a bit for now as to what I mean. And then we can use the slide to do what we have to do. So as I said, you would take the positional values. When we say the positional values, the 2 raised to the power 0, the 2 raised to the power 1, that's it. And then you multiply them with each number. That means that I am going to multiply this 1 here with this 1 over here with this 0 with that, this 1 with that, this 2, 1 here with that, 0 with that, 1 with that, 0 with this. Now, once I do that, this is what I would get from there. Over here, it is 1 times 128, this times 0, this times this, 0 times this will give me 0, 1 times 8 will give me 1, 1 times 4 will give me 4, 0 times this will give me 0, 1 times this will give me 1. That's 1 times 1. So when I add this up in normal arithmetic, whatever I'll get would give me my answer in base what? 10. Is that clear, please?
Yes, please.
The rest of you, are you there?
Yes, please.
Yes, sir.
Yes.
Please feel free to, as I told you at the beginning of the class last week, the school fees, no one pays more than anybody. So if you have something in which you want to say or wants to go over, you have to say it. You are not in the primary school anymore. So we are just here to learn, right? And everything else is secondary. So the most important thing to me, and again, I want to make it clear, to me, is that we have a very good understanding of what we are doing. If you want something, we want us to go over, say it now, because when we skip it, coming back is very difficult. So once we don't understand anything, it is very good we solve it where we are before we move on to the next place. So how would we do decimal to hexadecimal conversion? Let's say 13010, and I want to change it into hexadecimal. How will I do this? I will divide by 16. So 16 divided by 830 would give me 51. Remember what? 14. 14 is E in hexadecimal. So it means that my remainder is going to be what? E, not 14. I'll divide by 16 again. It will give me 3, remainder 3. In hexadecimal, you can have what? 3. So it is acceptable. If I divide 3 by 16, I will get 0, remainder what? 3. That is, let me put it this way. Over here, what we are saying is this 16 here times 5,1 or times 5,1 should give me a number that is close to 830. And that number, when I add 14 to it, then I'll get 830. So the 51 here is the closest number I can get to when I multiply by 16. So the remainder is what? 14. If I have 16 here, 16 times 3 would give me the closest number I'll get to 51. Then there will be a remainder of what? 3. If I have 3 here, what is the closest number I can get to? Is when I multiply 16 to 0, I'll get 0. So there will be a remainder of what? 3. And remember, when you get to 0, you can't go again. So you just have to write your answer. And where did we say our most significant bit starts from? Is it from the top or the bottom?
Top.
Are you sure? I remember saying that you write it from the bottom to the top. That means our most significant bit is the one at the what? Bottom. That means that if I was writing this, it would be 33E16. Are we clear of what we are doing?
Yes, please.
Okay. How will I then convert from hexadecimal to a decimal? So again, I will have to do positional values. So 16 raised to the power 0, 16 raised to the power 1, 16 raised to the power 2, 16 raised to the power 3. And then I'll multiply each by the one in which is on is at its position. So f times 16 raised to the power 0, 4 times 16 raised to the power 1, b times 16 raised to the power 2, and then 3 times 16 raised to the power what? 3. And whatever you get as your answer for each of the columns, you would then go and what? Add them all together. And your answer would be in base 10. How am I going to convert from base 2 to hexadecimal? So for that, if I don't want to write any mathematics or lines of math, I can use substitution code. Substitution code means that if I have 0 in binary, it is going to be 0000 in hexadecimal. If I have 1 in hexadecimal, it's going to be 0001 in binary. So I'll just look for the numbers and substitute with their equivalent in hexadecimal. Are there any questions so far? There is a very important topic we have to learn today. That topic has to do with ones and twos complement. What is a ones complement? What is a twos complement? So ones and twos complement is the computer's way of finding out numbers which are positive and negative. You see, there are times in which when you look at how a computer operates, how a computer does the things in which it does, how the computer is able to come up with the things in which it comes up with, remember something very carefully, that the computer is like a child. And if you take even us, me and you, as human beings, if I come to you and tell you, oh, this is a negative number, how do you know it's a negative number? Normally, what you do is just take the number and put a minus beside it. Then to you, you think it is a negative number, but that is the representation of the negative number to you. How does the computer know that this number is negative? The computer can't put a minus sign in front of it, because at its basic level, it is only ones and zeros. Hence, it doesn't have a minus number to put on it. Think of it very carefully. The computer doesn't have a minus to put on it to say, oh, this is -1, this is -2. There is no minus in its world. So how does the computer know that this number you are taking, make it negative? This number you are taking, make it positive. How does it know that? So the two's complement is the computer's way of discovering if a number is positive or negative. What is the structure of the two's complement? The structure. One second, I'm coming. I want to see if I can get a diagram that would better represent what we are doing. Then I'll show you the diagram. Okay, I've gotten some diagrams. In which I will show you later on. Yeah. So, how do we rationalize two's complement? First of all, we would need to do certain things. We first of all have to know the most significant bit. If I have 0, 1, 0, 0, like this, what is the most significant bit? Is it, or let me do it this way. Let me do it this way. What is the most significant bit? Is it this one?
One.
Or this one? Is the one. So the one here is the most significant bit. Okay. 1 second. So the 1 here is the most significant bit. Now, the 1, which is the most significant bit, indicates the positivity or negativity of the number. That is the first bit. The first bit, into brackets, the most significant bit, is the signal bit. It signals to the computer if the number is positive or negative. That is, if the number here is 0, then it means that the number is what? Positive. If the number is 1, then the number is what? Negative. It is not part of the numbers. What I mean is this. Over here, if I have 0, 1, 0, 0, in addition to this, here, because 1 here is positive, it means that this here is a negative number. So this 1 in front here, so that the rest, all of this 1 here is the number. This is just me indicating if the number is positive or what? Negative. If I have 0, 1, 0, 0 here, this side here shows me the number, and this side here shows me if the number is positive or what? Negative. Again, let's think of it in a very systematic way. And if you are thinking of this from a very systematic point, we can see that if I come to you and tell you, oh, this number here is a positive, then it's a positive 100, negative 40. How do you know it is negative 40? From your childhood, you just put a minus sign there and say this is negative 40. How is the computer supposed to know? How can the computer tell if the number you are putting there is positive or negative? How is the computer supposed to know? How can it tell? So it uses the information around him that it can use. What can it use? It uses bits, so ones and zeros. So for the computer, it is saying that, oh, if I have a number, the first bit, that is the most significant bit. If it is a 1, then that means that number is negative. If it is a 0, then that number is what? Positive. It also means that the remaining numbers represent the magnitude of the number. So the remaining numbers will tell you, oh, this is -4, +5, negative this, positive this. The remaining numbers will tell you the weight of the what? Number. Does that make sense, please?
Yes.
Hello, can you please hear? Are you there, guys there?
Yes.
How will I convert a number from a positive to a negative number then? How will I implement a ones, a two's complement on a number? How will I flip it so that I know that this number, this is positive, this is negative? How will I convert from a positive number to a negative number? How will I do that? First of all, I would need to convert a number to its negative 2 complements. And how will I do this? I would need to flip all the bits That is, wherever I see 0, I'll put 1 there. Wherever I see 1, I'll put what? 0 there. When I'm done, then I'll add 1 to it. Let's have an example. Over here, I have 3 in binary. 3 in binary is 0, 0, 1, 1. So this is what I have in binary. Now, I have been given a question. Write the 2's complement of this. That is, they want me to write the negative number of this. First, I have to flip all the binary numbers. I have to flip all the binary numbers. So in flipping, I am going to have 1, 1, 0, 0. I flipped it. So this is step 1. Flip numbers. Step 2. I'm supposed to add 1 to the number in which I have what? Flipped. So here I'll have 1, 1, 0, 0 plus what? 1. This would give me 1, 1, 0, 0, 8, 1, 1, 0, 1. That means that 0, 1, 1, sorry, 0, 0, 1, 1, which is 3, is going to be equal to 1, 1, 0, 1, which is minus what? 3. How can I convert from a negative number to a positive number? I will take the number I want to convert. I will flip it. So here, when I flip it, I will have 0, 0, 1, 0. And then when I'm done flipping it, I will add what? 1. If I add 1 to 0, 0, 1, 0, I'll get 0, 0, 1, 1. Doesn't this look like this one here? So again, the 2's complement is the computer's way of identifying positive and negative numbers. Why do we use the 2 complement? Why is the 2 complement very, very popular when people are building computers? They are very, very popular because, number 1, unified arithmetic. Addition and subtraction use the same circuitry. Subtraction is performed by adding the 2's complement of the subtracand. So because the mechanism for addition and subtraction are the same, it makes it easier for the computer to implement this in its operation. There is no ambiguity. That is, if I want to calculate the positive number of a number or the negative of the number of a number, using this method, I will never get anything which would not give me the correct answer. I'll always get the correct answer. If I want to convert from positive to negative, negative to positive, no matter what I do, the answer and result is always going to be the same. And the third one is that it is simply simplified. It's simple. If I want to make a negative number, change everything and then just add one. How simple can you get? How difficult is that? The simplification of it is very, very nice. You don't need to create a mechanism to do that. You can just use what you have. Are we okay with that? Another topic we are supposed to treat today has to do with the Boolean algebra. And that's talking about the logical gates. The logical gates provide us with a way where we can write logical expressions to the computer's board for the computer to use to think. We don't always think of this, but the thinking we do is based on a thinking pattern. If I wake up, I'll do this. If I don't do this, I'll go here. If I have to come back, I'll come and do this. If I do this, I'll do this. No, if I have this, then I will change. If this happens, then I'll go and do this. All of these things are based on logical patterns in which the computer is supposed to think of and utilize. Therefore, the logical gates provide you with a logical pattern you can think of and utilize. The first logical gate we have to learn is the NOT gate. The NOT gate can also be called the inverter. The symbols on the screen show you how they are drawn and how they look like. The diagram on the screen shows you that for you to have a NOT gate, there are only two possibilities of data that will provide you with the NOT gate. It is either your information is going to be true or false. That is either going to be a 1 or a 0. So you can see that for the input for a NOT gate over here, let me solve this. The input for a NOT gate over here, the line coming into it is only 1. Hence, I can either have on this line A being 0 or A being 1. That means the possibility of data coming in here is only 2. How do I know it is 2? Because it is 2 raised to the power 1. 2 raised to the power 1 is 2. Hence, the possibility of data coming into this system here is going to be 1 and 0. The job of the inverter is that if it is 0 coming in here, what will come out over here is going to be what? 1. And if it is 1 coming in here, what will come out over here is going to be what? 0. We have the AND gate. The AND gate presents us with a logical expression where it checks 2 inputs. So again, 2 raised to the power 2 would give me 4. So you can see that over here I have 1, 2, 3, 4 inputs for my expression. In this expression, I can have the possibility whereby input A, that is this one here, is 0, and input B, that is this one here, is also what? 0. I can have the possibility where input A is 0 and input B is what? 1. I can have the possibility where input A is 1 and input B is what? 0. Or both of them could be what? 1, 1. And they are saying that when you have inputs coming in here, only one input will come out here. And the one output which will come out over here can only be 1 when both of these two things here are 1. So you can see that over here, when this is 0 and this is 0, I have 0. When this is 0 and this is 1, I have 0. When this is 1 and this is 0, I have 0. But when this is 1 and this is 1, I have 1. Are there any questions so far? Marvelous. We have the NAND gate. The NAND gate is a combination of the inverter and the AND gate. The NAND gate is you taking the answer you got from the AND gate and negating it. So the AND gate is saying that for you to be true, both here and here both have to be what? True. But with the NAND gate, it would negate the answer. Hence, you can see that all answers are true. But when both of them are true, then I'll get a what? A false. We have the OR gate. The OR gate also presents us with the scenario whereby I either have both things being true or one of them can be true for my whole thing to be true. I also have the NOR gate. The NOR gate means that I am negating the OR gate. So OR gate is saying one of them has to be true. But the NOR gate means that the moment one of them is true, I'll get false. When both of them are true, I'll guess what? True. We have the exclusive NOR. The exclusive NOR is saying that I only need one item to be true. If both of them are true, be false. If both of them are false, be false. So you can see that here, when one of A and B is true, I'll get true for everything in which I am doing. Are we okay, please? And the final thing we'll talk about today is the exclusive NOR. And the exclusive NOR means that if I have both of my items being false, then my answer will be false. If both of my items are true, then my answer will be true. But if one of them is false and the other one is true, then my total answer is going to be what? False. Next week, when we arrive here, we'll begin with Boolean algebra and we'll start looking at the Boolean expressions and how we can draw the circuit diagrams and then solve questions on the circuit diagrams. Are there any questions, please? That's wonderful. If there are no questions, As always, I'll make the recording available to you in your group, and we'll meet again next week. I think next week will be the last time we'll meet online. Then from there, we'll continue to meet face to face.
Yes, sir.
Thank you
But
so
sir,
much for
can we have
coming.
the slides as well?
Yeah, you can have the slide.
Okay, thank
Now,
you, sir.
book no one can hear you now. Best slide. Hey.
Thank you, sir.
No problem. You can have the slide, okay? Thank you all for coming today. We'll meet again next
Thank
week.
you so
Bye-bye.
much, sir.